Hello and welcome back. Today what I want to do is go over bending moment diagrams and see how we can solve those in a quick and easy manner with minimal calculations. To do this we will need the shear force diagrams. That will make our life easier, and it will also help us identify where we need to find our moments. So if you haven't watched that already, please go and do that. I'll link that below. But if you have, let's just continue. Before we do that, I want to caveat, as I did last time, if you have been asked to find the equations for the bending moment, or if you need them for something like finding displacements, then you have to do the full thing. If not, and you just need a quick and dirty method to find the bending moments, then you're in the right place. Now, before we do that, I want to remind us, what are the shapes that we're looking for the moment? Let's look at this little diagram that I've prepared to show us the shape. If we start off by looking at a point load, we already discussed last week that if we have a point load, then our shear is going to be constant, like steps, right? The rank of the moment is going to be 1 above that. So if the shear is constant, our moment is going to be linear, just like shown in this diagram here. If, on the other hand, we have a UDL, so uniformly distributed load, we've already discussed that the shear is going to be 1 rank above, so the shear is going to be linear, and the moment is going to be 1 rank above that. So imagine integrating that shear. So if you integrate a linear load, a function of x, then you get a function that is x squared parabolic. And if we have a distributed load, a random one, that already gives us parabolic shear because it was a function of x, so 1 rank above gives us a function of x squared, a parabola, then the moment in this case is also going to be parabolic, but it'll be a function of x cubed. So from this little diagram, we already know by looking at the forces that we have on our beams what kind of shape our moment needs to be. So now that we've got all of that out of the way, we're going to look at the same 5 examples that we looked at in shear, and then we'll look at all kinds of things that you should be able to conclude from your load pattern, your shear force, and your moments. Let's get to it. So we're going to start off with the exact first example from last week. It was a simply supported beam. In this case, I only have point loads. I've already found the reactions, I've already found the shear, and I can already see the only point loads here, and therefore my shear is just constant numbers in steps, as you can see here. What I've done is I have taken down interesting points, so when there are jumps in shear or when the shear crosses 0, and I've brought them down and prepared a line for my bending moment diagram. And just a reminder, I am using this sign convention that we discussed, and my main thing here is I'm always going to draw my moment on the tension side. So the main idea here is to do this quickly with minimal calculations. So looking at this pattern, I know that I have to start my moment from 0. So I can draw that on. Now, when I look essentially from left to right, and it's a bit like covering up everything that is irrelevant. If I look at my beam here, what I'm doing now is I'm just looking from A to B, and anything that I don't need is irrelevant. So really, I start off by taking out this section and just looking at that. And if I look at that, I can see that when I reach B, I've got a moment of 100 times 3, so that's a moment of 300. And I guess my only thing is, I know it's 300, just going to write that there, kilonewton meters at B. And I guess my only question is, do I draw it on the top or on the bottom? So just a little reminder, if I look back at my sign convention, if this moment, according to my sign convention, came out as positive, I can see that tension is on the bottom. That is what happens here, but let me just kind of show you. I've had a force of 100. I've assumed that this is my moment, and I can see here that if I were to write the equation, I would have m minus 100 times 3 at point B equals 0. So m would be 300 kilonewton meters, as I've already discovered. And since it's positive, means pulling on the bottom, tension on the bottom, pushing at the top, compression on the top, I draw it on the bottom. I draw it on the tension side. Okay, so I've got 300 kilonewton meters here. I also know that this is a point load. I've got a constant shear, and therefore this moment has to be linear. So it's just a straight line in between them, like that. If I continue to point C, I can do it in two ways. The easiest way is actually to go from point D backwards. At point D, I know that my moment is 0, and at point C, I know that I'm going to have 80 times 3, so 240. If I do the same kind of exercise to figure out if it's tension or compression, I can look here, I've got 80 force, this time I'm starting in this way, and I'm assuming obviously that my moment is like that, which also gives me tension on the bottom, and I can see that these two are opposing in direction, so it'll be a positive moment, and I can draw here 240 kilonewton meters and a straight line in between them like that, and obviously I'm left with this section in between them. Now there can't be a jump in moment. You will only ever get a jump in moment when you have a concentrated moment. Other than that, you will never get a jump in moment, and therefore I need to meet between 300 and 240 with a straight line. And that's it. I've found the bending moment diagram with very minimal calculations, just to kind of double check the side I need to draw on. Now, a few interesting things to note. We have already discussed the shape, right? This is all going to be linear lines. The other thing to note is here, where my shear crosses 0, I can expect to get max or min moment, and that indeed happens. Another thing to note is that where there is a jump in my shear, there is a change of slope for my moment, and we can see that here and here. So a few interesting things to note, but apart from that, that was pretty quick and easy, wasn't it? So hopefully that was clear. Let's move on to doing a very similar thing, so a point load with a cantilever beam. Let's just try and remember those few things. What happens when there is a change in the shear force, where we can expect jumps and where we can expect changes of slope, and what kind of shape the bending moment needs to be. Let's have a look at the next example. So example number 2 is this cantilever beam with just a point load at the very end. We've solved the reactions, so there is a moment and a shear reaction at A. We can see here. We've already found the shear force, and just like before, because there were only point loads, this is just a constant, which once again means that my bending moment has to be linear, right? It's one rank above. If I was integrating a constant, I would get a function of x. Now, this one is pretty simple, because I know that at the very end I have to end with 0, and I know that at this point here, point A, I need to start with that moment. So remember how I said there'd only ever be a jump in moment if we've got a concentrated moment? Well, here we've got a concentrated moment. And let's have a quick think. This moment here, I'm just drawing the moment right now. What is it doing? It is pulling the top, right? So it's creating tension on the top of the beam, and it's pushing the bottom, so creating compression at the bottom. If I draw on the tension side, that means I need to draw on the top. So I already know what the moment is there. It's 120. Let's draw that in, 120 kilonewton meters. I end at 0. There's nothing happening along the beam, right? There's no additional force that would mean a change of slope for the moment, and there is no concentrated moment. So I just need to draw that straight line between the 120 and 0. So let's do that and finish this moment off. And there we have it. Now that we've had a look at point loads, let's look at two examples of UDLs, one in a simply supported beam and one in a cantilever beam. So starting off with this simply supported beam, as we can see here, I've already got the shear force, and this shear force is a function of x, right? It's linear, which means that my bending moment is going to be parabolic, right? It's going to have to be a function of x squared. I also know that here at this point A and at this point, let's call it B, the moment has to be 0, right? There's no jump in moment. Therefore, at the free ends, I have to start at 0. The other thing that I want to note is that just here at this point, I can see that the shear crosses zero. Now, when the shear crosses zero, it means that I get my max or minimum moment. And that's it. If I can find what that moment is at this point here, where the shear is zero, and I know that that's the max, I can go on to draw the full moment. So let's do that. Now, just to make sure that I don't make any mistakes, I'm going to quickly just draw out what I need to take into account. I've got this force of 54, I've got this UDL of 12, and I'm looking what my moment here is just in the middle where that shear force is 0, so at 4.5 meters. I can calculate that quickly on a calculator. I'm just going to write it out here so it's clear to everyone. So I've got moment m, then I've got minus 54 times 4.5, and then I've got the UDL contributing a positive moment, so plus 12 times 4.5, that gives me the force, and then times 4.5 divided by 2, that gives me the distance, equals 0, and m will work out as 121.5 kilonewton meters. So that's the only little calculation I need to do. Is it on the top or bottom? Well, it came out as positive, which means that this direction that I assumed is correct, which means pulling at the bottom, so tension on the bottom, pushing at the top, compression on the top. So I draw it on the tension side. So what I need to do now is just draw on this side here 121.5 kilonewton meters. It's going to be parabolic with a maximum at the 121.5. So something like that. And that's this example finished as well. So once again, note, zero moment at the free ends, a parabola function of x squared, and maximum moment where my shear passes through zero. Moving on to my next UDL, which is this time on a cantilever. I've already found the reactions, already found my shear diagram. As I mentioned before, this is a function of x, so this has to be a parabola x squared. And once again, it is pretty simple here. I know that I have 0 at this end, and I know at the A end I have 40 kilonewton meters. If I look at the shape, I can see that this moment is pulling on the top, so tension's on the top. So I can draw my 40 kilonewton meters here, and I have to end in 0. And it's parabolic. Now, we have discussed this before, but of course, it can be parabolic this way, or it can be parabolic that way. Now, the easiest way to go from that, if I'm not looking at maths, is that whenever I have a UDL, the UDL is like the wind, and my beam is like the sail. So if I just use that analogy, I know that this is how my bending moment is going to look like. And that's it. Solved. So I've solved point loads and I've solved UDLs all separately. For our last exercise, let's have a look at what happens when they're combined together. This is a little bit trickier. I might have to do a few little hand calcs, but nothing too strenuous. Let's see how we put everything that we've learnt together, how we identify the shapes of the moments, how we identify where some interesting points might be, and let's get to it. So for this last exercise, I've got a bit of a combination. I had this angled force here, which I separated into components. I've got this UDL of 6 kilonewton per meters, and I've already found the reactions. I've already found the shear force diagram. Now note that in the shear force diagram, in sections where I just had point loads, we can see this usual kind of step design of my shear force. Okay, so these are just constant shears. But when I reach my UDL, we can see that that changes, doesn't it? I go to getting a linear line. So I know that here on my bending moment, this section here, right, up until here, these bits should just be linear or functions of x, and this bit here should be parabolic, function of x squared. I'm taking down a few interesting points. So you can see here that I've already put in wherever there's a change in my shear. But the other interesting point is going to be this point here that I'm adding in. Let's actually add it in another colour to make it clearer. This point here. And this point is going to be important because here I can see that my shear passes through 0. So this is probably going to be where my maximum moment is. Let's look at this together. I'm going to start off from point A. So I'm going to start off from here. Let's call this A, B, C, D, and E, just so we're talking in the same terms. And let's start off at point A. So from point A, if I just cut through A and B and want to find the moment at B, I've just got 17.68 times 2 meters, and that gives me 35.36. Once again, I can already tell the direction. I can tell that tension is going to be on the bottom. If I don't want to do calculations and I don't want to draw a cut, I just want to look at it. Let's just look at it in this way. I've got a diving board, an upside down one, and somebody standing here, right? This board would take on this shape, wouldn't it? It would go like that, meaning that on this side, the board would get longer, and on this side, it would get shorter. The side that it gets longer is my tension side, and that is the side I want to draw my moment on. So in this case, I'm going to draw here 35.36. And this is a linear line, so I'm just going to go from 0 to that line in a straight line. Now I want to find my moment at C. So to find my moment at C, I can just say that I've got 17.68. Now I know that that is already meaning, if this is positive, it means that tension is on the same side, times 4 this time, and then minus, because it's creating a moment in the different direction, 15.58 times 2. And if I calculate that, I get 39.56 kilonewton meters. So just a tiny little change here, right? So 39.56, and once again, a straight line between them. And now I want to find what is the maximum moment at D, right? So I want to look at point D and figure out what the moment is there, because I know that that is going to be the maximum moment that I have in this beam. The question is though, where is D? Now if I had calculated the equations like I showed in previous tutorials, that would be really easy to find from the equations. But this time I do not have the equations. So I'm going to rely on geometry to do that. And this is what I'm going to do. I'm just going to use similar triangles. I'm going to draw out my shear. So I've got 21.9 here. I've got 2.1 here. I've got a straight line between them. I know that this is linear, so it's going to be the same angle. I know that this whole thing is 4 meters, and I'm just going to say that this little bit here till 0 is going to be x, and therefore this bit here is 4 minus x. And if I just look at solving similar triangles, which I'm sure you all know, I've got 2.1 over x has to equal 21.9 over 4 minus x. If I write out that equation just by multiplying in these directions, I get that 2.1 times 4 minus x equals 21.9 times x, and I can find out that x equals 0.35 meters. Okay, so this little distance here is 0.35 meters. And now all that is left for me to do is figure out what that maximum moment is at D. So I can go from this direction, so I can go from E to D, which would actually be quite simple, or I can go all the way from A. Let's go from E to D. So if I go from E to D, I've got a reaction force of 21.9, I've got a UDL of 6, this is the moment that I need to find, and the distance 4 minus 0.35 is 4.65 meters. So my moment, which is minus it according to this direction, plus 21.9 times 4.65, and minus 6 times 4.65, that gives me the force, and then times 4.65 divided by 2, that gives me the distance. And if I solve that, I get 39.72 kilonewton meters. So not a massive increase from the moment I had. So I'm just going to draw that in a different colour so it'd be a bit clearer. Not a huge, this is a bit of an exaggerated drawing, but that is 39.72. And I need to end here in 0, right? And this is parabolic. Now, there has not been a change of slope here. So I need to kind of continue here in the same slope, go down a little bit to reach that max moment and then go back to 0. This is parabolic, and this bit here has just been linear function of x. So let's have a look at the things to note. Linear, as we said, and parabolic. Maximum when the shear passes through 0. Change of slope when I had a change in the shear, so here and here, but not here, right? Here there was not a change in shear, so although I had a maximum here and I went down to 0, here there was no change in slope. So just a few interesting things to point out before we summarize. So in this session, we discussed how to find the bending moments when we already have shear and reaction and we just want to find it with as little equations as needed. We've seen what shape the bending moment needs to be, where it needs to be max or min, where to find a change in slope, and where we can expect any jumps. I hope that was helpful, and I hope to see you again for some more structural engineering. In the meanwhile, bye for now.